Welcome to Moo Moo Math and Science. This is Earth Science Review Part 2, and we will cover the water cycle, the ocean floor, atmosphere layers, conduction, convection, and radiation, global winds, weather fronts, how hurricanes are formed, and the distribution of water on planet Earth. So, let's get started. In order to help you understand and remember the hydrologic cycle, also called the water cycle, I will show you a quick demo for these 9 steps: evaporation, condensation, precipitation, transpiration, infiltration, groundwater, aquifer, runoff, and accumulation. So let's start with evaporation. Evaporation occurs when a liquid turns to gas. With this glass of water and the heat from the lamp, evaporation is occurring. The problem is you can't see the evaporation. Now, if I take hot water and pour it in the bottle, the water vapor will cool and you'll have condensation. You can see the condensation on the sides of the bottle. This occurs in real life when evaporation cools and attaches to small particles in the atmosphere, and clouds may form. When you get enough condensation, some of the liquid will fall, as you can see falling off the sides of the bottle. In real life, this can be rain, or snow, or many other forms. Next, transpiration is when plants release water vapor. You can see the water vapor on the sides of the bottle. This vapor comes from the leaves and the stems of the plant when it releases it. Plants do not use all the water that it absorbs from its roots, and it releases some in the form of vapor. Next, infiltration is when water moves down through rocks and sand, etc. You can see the water infiltrate through these rocks. This water that moves into the ground is called groundwater. Much of this groundwater will move into an aquifer, which is represented by the sponge. Think of an aquifer as a huge sponge made of rocks. Remember, some aquifers, like the one in Florida, is as large as the entire state. The ground will not absorb all of the precipitation, and some will run off like this pan that is filled with rocks and soil. This is called runoff, and sometimes it leads to flooding. This runoff may end up in a lake or an ocean, which are examples of accumulation. Remember, during the water cycle, it does not go in a nice circle, but moves in many different directions over and over again. It is made up of various landscapes, including mountains, valleys, and plains. These underwater surfaces of the ocean floor are located from the shallow part of the ocean to its deepest part. The continental shelf is the underwater edge of the continent. It extends from the shore to a depth of about 600 feet and has a gentle slope. About 50 miles from the shore is a steep slope called the continental slope. The continental slope leads from the continental shelf towards the seafloor and is also deeper than the shelf. About 12 or 13 miles away from the shore into the ocean is the continental rise. The continental rise is a buildup of sediment and sand on the ocean floor at the bottom of the continental slope. It is usually sand and mud that stretches from the slope down to the deep sea floor. One of the flattest places on Earth is at the end of the continental rise. The abyssal plain is a large area of flat land that covers almost half the ocean. These were formed when most of the hills and the valleys at the bottom of the ocean were buried under a layer of sand and mud a long time ago. There may also be huge underwater mountains called seamounts. The peak rises hundreds of miles from the ocean floor. Seamounts are also volcanoes that were formed in the same way as a volcano on land. Hot molten rock rose from inside the Earth's surface and cooled into a solid. Sometimes a seamount may appear as an island. The Hawaiian Islands are an example of a chain of islands formed by seamounts. There are also trenches located at the ocean floor. An ocean trench is a V-shaped valley that is long and narrow, and they are the deepest parts on Earth. They may extend 5 or 6 miles below sea level. Mount Everest would fit inside the largest trench and would still be over a mile below the surface of the Earth. The largest deep-sea trench is about 7 miles deep. Trenches are so deep, sunlight will never reach these areas. In the middle of the Atlantic Ocean is a huge mountain range rising above the ocean floor. This is known as the mid-ocean ridge. The mid-ocean ridge is part of a chain of mountains called the mid-ocean ridges. These ridges wind their way through all the world's major oceans. The mid-ocean ridge extends the entire length of the Atlantic Ocean. The mountain ranges were also formed by volcanoes and molten rock that cooled and hardened. Finally, the ocean floor is home to hot springs called seafloor vents. These vents are formed when seawater trickles down from newly formed ocean crust. Eventually, the water becomes saturated with minerals and it boils out of a vent into the crust. The Earth is surrounded by a protective atmosphere. It keeps our Earth warm and protects us from comets and meteors. This atmosphere can be divided into 4 individual layers, separated by changes in air temperatures. These layers are the troposphere, the stratosphere, the mesosphere, and the thermosphere. The troposphere is composed of 78% nitrogen, 21% oxygen, and 1% other gases, including argon. It is a layer where we live, and it's a layer in which weather occurs. The atmosphere in the troposphere presses down with a great deal of pressure each day, but many times we don't even notice this. In fact, this Coke can is crushed by our atmosphere. As you go upward in the troposphere, the temperature drops. This is called the lapse rate, and the temperature drops 3 degrees Fahrenheit for every 1,000 feet in elevation. For example, in my state, Augusta, with an elevation of 136 feet, has an average high temperature of 77 degrees. And Blairsville is over 3,000 feet in elevation and has an average high temperature of 68 degrees. The troposphere extends from the ground to about 10 kilometers. This is equal to 25 laps around a track. At the very top of the troposphere, temperatures drop to around negative 50 degrees Celsius. This begins our next layer called the stratosphere. The ozone layer is found in the stratosphere. The ozone layer protects us from ultraviolet light rays given off from the sun. And as you get higher in the stratosphere, the temperature actually gets warmer. This is because of the ozone layer absorbs ultraviolet rays and warms up the stratosphere. At 50 kilometers above the Earth, we move to the next layer called the mesosphere. The mesosphere gets colder as you go up. In fact, it is the coldest layer and can have temperatures as low as negative 90 degrees Celsius. This mesosphere protects the Earth from space junk because of the ice crystals burn up the space junk as it moves through it, and extends to about 80 kilometers high. And finally, you have the thermosphere. This is very hot. In fact, it's the hottest layer, and you can have temperatures between 500 and 1500 degrees Celsius at the very top. 2 additional layers of our atmosphere are the ionosphere, which is full of electrically charged atoms and is the home of the northern and southern lights, and it also reflects back radio waves. The exosphere is the outermost layer of our atmosphere and stretches almost 10,000 kilometers into space. It is composed of helium and several heavier molecules, including nitrogen, oxygen, and carbon dioxide, but they're spread very far apart. It is also home to the satellites. Each layer is classified according to temperature. As you gain elevation in the troposphere, the temperature actually drops. The temperature range is from around 15 degrees Celsius to negative 45 to 50 degrees Celsius at the top. The temperature of the stratosphere actually gets warmer with elevation and ranges from minus 45 to 50 degrees Celsius at the bottom to 0 degrees Celsius at the top. The mesosphere is similar to the troposphere, and the temperature increases with elevation. The temperature ranges from 0 degrees Celsius to negative 90 degrees Celsius at the top. And finally, the thermosphere actually gets warmer with elevation. The temperature ranges from negative 90 degrees at the bottom to over 1500 degrees at the very, very top. Also, as you move from the troposphere to thermosphere, in other words, get higher in elevation, the atmospheric pressure decreases. So as you go up in elevation, the atmospheric pressure decreases. And as you go down in elevation, the atmospheric pressure increases. In fact, in 2002, Felix Baumgartner completed a free fall parachute jump from the stratosphere. And during this jump, he reached speeds of over 800 miles an hour and even broke the sound barrier. He was able to reach these speeds because the atmosphere was so thin that there was very little friction to slow him down. This water boiling, the heat of the fire, and cooking on the skillet are all examples of heat transfer. In simple terms, heat is the transfer of energy from objects of different temperatures. As objects warm up or cool down, their kinetic energy changes. Kinetic energy is the energy of motion. Temperature is a measure of the average kinetic energy of the particles in an object. As temperature increases, the energy of motion increases. As the water warms up and the temperature increases, you can see an increase in the movement. Heat can be transferred in at least three ways: conduction, convection, and radiation. Conduction is a process in which the transfer of heat takes place between objects by direct contact. It is most often associated with solids. The key to conduction is direct contact. The heat of the pan is transferred to the mini pizzas. The energy of the frying pan is transferred to the eggs. Notice that they are in direct contact. Convection is heat transferred by the movement of a fluid such as air or water when the heated fluid is caused to move away from the source of heat, carrying the energy with it. It occurs due to density. Lava lamps are examples of convection. As the liquid is heated, it rises and falls as it heats and cools. As the paper burns, the air is heated up and begins to rise. The burning paper is swept up in the convection current, cools, and falls back down. These beans are another example of convection. As the beans warm up, they rise and then cool and fall back down, and repeat this over and over again. Radiation heat is transmitted without any physical contact between objects. Watch how the temperature of the lamp is transferred to the thermometer without touching it. These alligators and lizards use radiation from the sun to warm their bodies. In ancient times, sailors realized that certain winds are always present at certain locations on Earth. In fact, many sailors became rich by using the trade winds to travel from one city to another. Why do we have these winds on Earth? Welcome to Moo Math and Science and Global Winds. In order to understand global winds, we need to learn some basic facts. Due to how the Earth tilts on its axis, the sun's rays strike the Earth at different angles. This results in unequal heating of the Earth's surface. For example, the equator receives more direct sunlight than places such as the Arctic Pole. This is why the equatorial region is so much warmer than the Arctic and Antarctic poles. Cold air is denser than warm air. It sinks, creating high-pressure areas. Warm air is less dense and rises, creating low-pressure pockets. Air will always flow from high-pressure areas to low-pressure areas. Because the Earth spins, anything that floats above the Earth's surface, such as air, appears to follow a curved pattern of movement. This is called the Coriolis effect. The Coriolis effect heavily impacts the travel pattern of global winds. In the northern hemisphere, air moving from north to south deflects to the left. From the equator to the poles, air deflects to the right. Now let's put all this together and look at some global winds. First, we will label the Earth. The direction of the global winds change every 30 degrees on Earth. You can see I have the Earth labeled 90, 60, 30, and 0 degrees in the northern and southern hemisphere. At 90 degrees, the air is very cold and dense and creates a high pressure system. At 60 degrees, the air is warmer, resulting in a low pressure system. At 30 degrees, the air is cooler than it is at the equator, creating a high pressure system. It is very hot at the equator, and the warm air creates a low pressure area once again. Notice the alternation between high pressure and low pressure areas. Every 30 degrees witnesses a pressure change. Next, remember that the Coriolis effect heavily impacts airflow. Wind systems will twist clockwise or counterclockwise under the Coriolis effect. In fact, this is what happens with the prevailing winds. There are three main prevailing belts: the prevailing westerlies, the trade winds, and the polar easterlies. The polar easterlies are the dominant winds found between 60 degrees of latitude and the poles of the Earth. Remember that air likes to move from high pressure areas to low pressure areas. So the wind will start from the poles at 90 degrees, areas of high pressure, and move down towards 60 degrees where the pressure is low. The prevailing westerlies are the dominant winds found between 30 and 60 degrees of latitude, and the Coriolis effect moves them from west to east. Hint: winds are always named from the direction that they start from. The trade winds will move from the high pressure area of 30 degrees towards the equator, which has low pressure, also called the tropical easterlies because they blow from east to west. Are there areas with little wind? The doldrums, also called the intertropical convergence zone, are such a place. At the equator, the air is very warm due to direct heating from the sun. Remember, hot air rises, and since the equator receives such intense sunlight, the air at the equator rises vertically like a hot air balloon instead of blowing horizontally. As a result, the doldrums, which are located between 0 degrees and 5 degrees of latitude, experience very little wind. The horse latitudes are located at 30 degrees north and south, also experience little wind. The horse latitudes are areas of high pressure, and thus winds go separate ways from one another, searching for pockets of low pressure. The prevailing westerlies will head towards 60 degrees of latitude, while the trade winds will head towards the equators. Sailors have tried to avoid areas like the doldrums and the horse latitudes because they wanted strong winds that would push their boat along. Our weather is constantly changing. You may have thunderstorms and rain one day, and then later in the week sunny clear skies, followed by cloudy light rain or even snow. Much of this weather occurs along the boundary of different air masses, which we call fronts. Welcome to Moo Moo Math and Science and a weather front chart. In this video, I will go through a simple chart and go over major points of fronts. Up first is a cold front. Here's the symbol. Notice it contains blue triangles. The air masses involved are cold air mass meets a warm air mass. The warm air mass is less dense than the cold air mass and rises quickly. The weather along a cold air mass may involve thunderstorms and possibly severe weather. As the front passes, you will see colder, more dry air and fair to clear skies. Next is a warm front, and here's the symbol. A warm front occurs when a warm mass of air will slowly rise above cooler or cold air. The weather along a warm front is generally cloudy weather and rain. However, if the air is very unstable, you may get a thunderstorm. As the warm front passes, you will see warmer, more humid air. An occluded front, here's the symbol. Notice that you have warm air sandwiched between cold air. An occluded front has three air masses involved. Warm air gets caught between two cold or cooler air masses. Along an occluded front, you can see rain or snow, and it may be heavy, or this front may have weather similar to a cold front, which will include thunderstorms. After an occluded front passes, you will have fair skies and cooler air. A stationary front, and here's the symbol, and a stationary front occurs when you have cold air mass and a warm air mass of equal density, and they collide, but because of the equal density, they remain stationary. A stationary front may bring several days of rain or snow. Depending on the wind direction, you may get warm or cooler air as the front passes in fair skies. Next, hurricanes. Where do they form? They form over warm oceans. The season is June 1st to November 30th, but they can occur outside of this window. Typical hurricanes are 300 miles wide, but the largest was 1,380 miles wide. How long do hurricanes last? On average, 12 to 30 hours. However, some have lasted up to 30 days. How do hurricanes form? First, you need the following ingredients: a group of thunderstorms that move over the ocean. Next, warm, moist water. In fact, the water needs to be roughly 80 degrees or higher. You also need unstable air that allows the moist air to rise. This rising air needs to be humid and rise up to 18,000 feet. This large amount of water vapor supplies latent heat and energy for the storm. Gentle winds in the upper atmosphere traveling at the same speed and direction help avoid ripping the storm apart. And you also need a high-pressure system in the upper atmosphere. All of this may come together to create a hurricane. What are the hazards? In addition to strong winds, you have flooding from the storm surge. What should you do? Evacuate. Leave. There's usually plenty of lead time to get out of town. If you can't, seek high ground. I'd like to talk about the global distribution of water. If you look at the Earth from space, it appears blue. That is because 71% of the Earth is water. But how is this water distributed? First, 96.5% of the water is found in oceans, streams, and bays. Next, 1.74% is found frozen in ice caps, glaciers, and permanent snow. 1.69% is found in groundwater. Water that is found on land will pass through rock until this rock becomes saturated. The point where the porous rock and saturated rock meet is the water table. However, not all of this underground water is fresh water. 0.93% is salty water or saline water, and 0.76 is fresh. Now we move down to soil moisture. 0.001% is found in soil moisture. Soil moisture is the water that is held in the spaces between soil particles. Surface soil moisture is the water that is the upper 10 centimeters of soil, whereas root zone soil is the water that is available to plants, and it is generally considered to be the upper 200 centimeters of soil. Coming in behind soil moisture is ground ice and permafrost, and that is 0.022%. Lakes make up 0.013%. However, not all of these are fresh water. Freshwater lakes make up 0.007%, and then salty or saline lakes are 0.006%. Moisture in the atmosphere accounts for 0.001% of the Earth's water. Swamp water accounts for 0.0008%. Rivers account for 0.0002%. And finally, biological water, which is water that surrounds a biomolecule like protein or DNA, accounts for 0.0001%. So there we go, how the water on Earth is distributed.